So we're going to do this with integration by parts to start with. So we're going to think of that as secant times secant squared. So since this integral we know fairly easily, we'll call the dv secant squared. And that means the u is going to be secant. So du will be secant tangent, and the v is going to be the tangent. So that's the beginning of our odyssey here. It goes on and on and on. So we're going to get u times v. So u times v is secant x tangent x minus the integral of v du. So here's our v and there's our du. So that's going to become a secant x times a tangent squared x dx. Well, this is like what we've been doing in that section 7.3. So what we want to do here is trade in the tangent squared. So we know that, well, maybe we know, sine squared plus cosine squared is 1. If you divide by cosine squared, we get that tangent squared plus 1 equals secant squared. So tangent squared is secant squared minus 1. You with me there? So this then becomes minus our integral. We'll have secant x times, and we're going to trade that in for secant squared x minus 1. So when we distribute, we're going to get minus the secant cubed. Oh no, that's where we started this whole mess. Plus an integral of secant x dx. It's gotten worse. No, it's gotten better. Because now we can say that, let's see, if I write everything down, we have this integral of secant cubed is equal to all of this. We can add this integral back over there, making 2 of those unknown integrals, which is going to be secant x tangent x plus this integral, which is that horrible natural log of secant x plus tangent x. Deep breath, divide everything by 2. And after all that, don't forget to tack on the plus c. Crazy. That comes up surprisingly often. So it's one that you just need to be familiar with. I got a feeling you may have to do that sometime.
Maybe I can just memorize it.
Yeah, good luck.
Make it easier.
Yeah, I don't know about that. Any other questions before we dive into one of the harder things that we do? What's that? That was a walk in the park. Trig substitution's tough. That's what we're going to try to do. Anything else?
15 on homework 59.
15 on homework 59. You know what that is?
The integral of x times sine squared x.
What do we want to do with this? I think what we have to do here is we have that power reducing formula for sine squared. So sine squared, I believe, is 1 minus the cosine of 2x all over 2.
Yeah.
Is that correct? So the problem is a sine squared. If we just had x sine x, that would be an integration by parts problem. But with the sine squared, we could trade the sine squared in for 1 minus cosine squared. And that's not going to help us. We still got the same issue. But by making this be just cosine to the first, we've got...
Integration by parts. Okay, I can do it.
You can do it from there.
I was not connecting the integration by parts.
Yeah. So one part you won't need integration by parts, but the other one you will still.
Cool. Thank you.
Oh, you let me off easy. I can do that. Anything else? I don't think anybody's going to ask you a question. Macy, do you have one? No, I thought you had that look. I thought you did.
I had 47 on the same homework,
Okay.
which was integral of sine 3x cosine 2x.
Yeah. Now this one, this takes us back to another of those formulas we used back in our AP prep days. You have to memorize them. But if you take out that sheet 7.3,
Can I
that
steal
has,
a hard copy?
sure can.
I'm sorry, Mr. Tree, did you say we will have to memorize this or we
You
won't?
will not have to
Oh, okay.
memorize this,
Okay,
no.
sorry, I thought you said we will. Yeah.
When you take the test on this, and by the way, we should talk about that. You can use this, it's sort of a formula sheet, not exactly, but just for the record here, trying to look ahead. You have Friday, we're going to take the chapter 6 test here. And a week from Friday, I believe we can go out in a blaze of glory here. So I think we can do this where we can take chapter 6 test this Friday, chapter 7 test next Friday, and the semester 1 final perhaps on that Friday before. What a great way to end 2020, huh?
Are you assigning homework over break? You should tell my dad. He is. By the second one, I'd be run down.
And I'll check on that to be sure, because I don't have it written down yet, but I think we might even be able to squeeze the final, but I'll let you know that.
If you don't, I will not. I agree with that, yes.
So are you with me there? Do you see that on the bottom? It says, we have a sine, cosine of different things. So the sine, cosine, sine mx, cosine
on the
nx,
very
see it there?
bottom. Oh, I see. Oh, I didn't even, okay.
Yeah, you need to use that.
I feel like those formulas would have helped.
I think so.
So for test day, we just bring this.
Yeah, well, there's going to be more too. So on test day,
Not this test. But the
not
next.
this test, because chapter 6 test, you won't need this. The chapter 7 test, you're going to need this. And then we're going to eventually, later this week, next week, we will do what's called integration by tables. So I will print you off this, it's 3 or 4 pages of tables of integrals. And you'll need that also. So there will be this part here, you can use throughout this test and you can use it throughout the final. The part with the integration of tables printed off, I think you'll use it on 1 page of the chapter 7 test. And that's it. You won't be able to use it on the other part of the test.
Will we get these on the AP test?
No, you will not have any of this stuff on the AP.
Oh, okay.
No, I mean, they won't ask you. This is not an AP topic. You might do something, like it would be reasonable to see something like this on an AP test, where you could say, oh, U is going to be sine X, DU is going to be the cosine, and you can make it into a power integral. That probably you could see, but the complexity of the ones we have done with all the different powers of secants and tangents and cosecants and cotangents and some of the crazy ones, that's not their emphasis. So I guess theoretically it could appear, but it would be very surprising. Yeah. But it's about exposure. Yeah. So, different colleges and universities teach different things in their Calc 2 classes. And this is, when you hopefully can test out of this, whatever school you go to will assume what they teach in their Calc 2. So some of the things that are not on the AP syllabus, some schools do expect you to have seen or be able to do. So this whole chapter really is one that isn't really, except for the integration by parts and the partial fractions, is not going to be on the AP test. And we'll do some more. We're going to do some applications in January when we come back, and we'll do things like work and fluid force and centroid, centers of mass, that they would never ask you that on an AP. But a lot of engineering colleges expect you to know how to do that from, what they would have taught you in Calc 2 if you'd been at their school. So we'll do it. So you'll get, hopefully anything anybody teaches anywhere in their Calc 2 you will have seen. So you should be well prepared. Yeah. This is the generic get out of jail free card for any Calc 2 class, hopefully. That's the intent anyway. Anything else? Okay, so we are going to talk about, I think this is one of the trickier things that we do. It's called trig substitution. Again, this is not an AP topic. So this will not, and it's not in our book because our book just teaches predominantly AP topics. So again, I have plagiarized another textbook for this. So this is known as trig substitution. I should say that on record. You can at least deny it if I just told it to you. Oh well. So the purpose of this is to solve integrals involving these kinds of radicals. So specific kinds of radicals. Things that are of the form the square root of a squared minus u squared, the square root of a squared plus u squared, and the square root of u squared minus a squared. So these, the things that come from the Pythagorean theorem. Okay, so depending on where you put the a and the u in a right triangle, then the third side would look like one of these things. Okay, and that's the idea behind it. And so we're exploring these relationships, so these are related to these. So we'll say these come from the trig relationships. That say cosine squared is 1 minus sine squared, and that secant squared is 1 plus tangent squared, and that tangent squared is secant squared minus 1. And so you can kind of see maybe where these radicals might come from when you solve for the tangent or the secant or the cosine. Okay, so what we're going to do is we're going to look at an integral, and then we're going to, based on what we see in the integral, what kind of radical we get, we're going to label the sides in our triangle. One side is going to be A, one side is going to be U, and the other side is going to be the radical. And then the radical will appear, they'll appear in different places, different positions in the triangle, depending on which radical we're going to try to match, to come up with. So I think the hard part, the trickiest part, is figuring out how to label the sides on your right triangle so that you get the three things that you want, that you get A, U, and the radical defined in terms of then a sine, a cosine, a tangent, a secant, a cotangent, and whatever I didn't say, cotangent. So that's kind of the tricky part. So I'm gonna show you a little bit about kind of why it works the way that it does. So in order to kind of justify that the domains work out the way that they should, so that it really is a valid substitution. So some of the stuff that I'm going to talk about here, you don't have to recreate. It's just, can you actually do the substitution? We're going to make a substitution. So at the end of the day, we're going to take an integral we can't do. We're going to draw a triangle, a right triangle. We'll label the sides so that one will be U, one will be A, and one will be whatever radical it is we're looking for. We'll name all of those in terms of trig functions. What's sine theta, cosine theta, tangent theta. The integral that had those radicals and x's in it will be replaced by an integral that has all trig functions and d theta. And the hope then is that that integral will become ones like we've been doing on that sheet 7.3. It's an integral we can do. We'll do the integral involving trig functions. And then once we have that integral, we'll go back to our triangle and the substitutions and go back to an answer that's going to involve the x's and all that stuff that we came from in the triangle. I know that sounds kind of weird, but we'll see how it goes. So, well, first of all, for integrals involving the square root of, what do I want to call this? My eyes get older. My head doesn't get any bigger, which it needs to be. So if we look at a squared minus u squared, so we're going to involve the square root of a squared minus u squared. So what we will do when we name this triangle, so we're going to draw our right triangle and we're going to put theta in one corner. Now, when we have, of our three radicals, there's one that has a plus sign in it, which I think then makes it the easiest to identify. One of these is a square root of a squared minus u squared. One's going to be a square root of u squared minus a squared. The one that precedes the minus sign is the one we're going to name as the hypotenuse. So its square root becomes the hypotenuse. So in the square root of a squared minus u squared, the hypotenuse will be a. In the square root of u squared minus a squared, the hypotenuse will be u. And in the square root of the sum, that radical will become the hypotenuse. And then it will work out. Now, the other two sides, one is going to be the u. The other one is going to be this radical. Now, as we do this, this is the part where I never remember which way to go. But always we're going to say that our x is going to involve either a sine or a tangent or a secant. So that is going to be our substitution. Now, it could be done using different ones. You could have x be a cosine theta or a cotangent or a cosecant, and it would still work out. But it's complicated enough, so generally everybody just agrees that we're going to try to make it be one of these. So that's going to be what drives where I put which of these in which spot. So I'm going to just guess, I don't know if I have it right. U and the radical a squared minus u squared. So when we solve for u, which is going to hold our x in it, so that might be x, just x, it might be something more than x, but that's got the x in it. So to solve for that, I want to pair it with the constant, not with the radical. So that would mean that the trig function that connects our angle theta with this thing that has our x in it and the constant would be opposite over hypotenuse is a sine, which is going to work because I want it to be a sine, a secant, or a tangent. If I had done this wrong, if I had labeled it here, just so you could see, you know, because sometimes this is how it is with me, it's trial and error. And I said, okay, if I want to match this up, this would
Good afternoon, Laramie High School. At this time, we will be conducting a lockout drill. Again, this is only a drill and only for practice, but this is a lockout drill. Remember, during a lockout drill, all students are to remain inside the class. Teachers, please bring all students inside, close any doors in your classroom, and then it's business as usual. Please do not let students enter or exit your room. During this drill at this time, if you're out in the hallways, please report to either back to class immediately or head down to the main office, and then hold those students in your classroom until the drill is over. Thanks again, and please remember this is a lockout drill.
So I asked him if we could just do a lockout drill till 3:30 today, so we'll see. So this, I would say, well, now here to connect this with this would be a cosine. I don't want a cosine. So then I would just say, oh, I just got to switch them because I put them in the wrong spots. And that happens to me about at least 50% of the time. So when we get to here, then what we can say is that the sine of theta is u over a, or u is a sine theta. that make sense so far? I mean, I don't know why we're doing this yet, but then we would also solve for the radical, because where this came from is some integral that had this radical in it. So again, we're going to pair it with the constant. So we would say that the cosine of theta is going to be that radical, that's our adjacent side, over the constant that's the hypotenuse. And so we would say then that a cosine of theta would be equal to our radical, square root of a squared minus u squared. Now what I want to talk about here is just the domains a little bit. If we were really doing an integral this way, we would have to get what the x is and then differentiate to find out what dx is. So we would replace the dx in our integral by something with the d theta in it. But we'll get to that eventually. Let me just talk a little bit here. So in this radical here, remember, for this to be defined, we need that this has to be a positive number. Right? That a squared minus u squared has to be positive, or else we can't take the square of a negative. So what that means is that u has to be in between what? So u has to be between a and negative a. Does that make sense? And if we're saying u is equal to a times sine theta, that's a perfect match. Because the biggest sign can be as 1, which would mean the biggest this could be is a times 1. And the smallest sign can be as negative 1, which means the smallest u could be is a times negative 1. So it's exactly what we want. So that's a great substitution. Anything else that I want to say? I think that's pretty much it. Now, back here, now what we want for this radical, so this radical has to be non-negative, because what this is the principal square root. So whatever we get out of here can't end up being a negative. So if we're setting it equal to a cosine theta, what we're going to say here, we're going to get everything we want out of u if our theta is between pi over 2 and negative pi over 2. So as long as we stay between negative pi over 2 and pi over 2, sine theta is going to do everything it can possibly do. We're going to get everything from negative 1 to positive 1 that sine does. And the good news is that interval, we're always to the right of the y-axis. So on that interval, cosine is always positive or 0, and so we're good to go. So the things we were worried about, is this going to be defined in this radical, is okay, and is this radical equal to a positive number is also okay, so that's going to work. Now you don't have to worry about that and try to duplicate this, but it's nice to know that somebody thought about that. Okay, okay so far, sort of. Okay, I'll come back and do some examples here. So the second thing, if we look at integrals that look like the square root of a squared plus u squared. So here, when we see this radical, we are going to label the hypotenuse the square root of a squared plus u squared. So that is going to be this, right? It's just Pythagorean. And that means the other two sides are going to have to be, one of them is going to be a and one's going to be u. Okay? And it really doesn't matter, except that we're going to try to make our u equal to a sine, a tangent, or a secant. So if I label it incorrectly and say u is here and a is there.
A sine, a cosine, or a tangent?
A sine, I want u to be a sine, a tangent, or a secant.
Okay.
Just those.
Okay.
But not a cosine, not a cosecant,
Okay.
not a cotangent. Not that it couldn't work, because it would still work, but that's not generally how it's done. So if I did this, then the trig function that connects our u, which holds the x in it, with the constant, would be adjacent over opposite would be a cotangent. I don't want that. So I did them wrong, so I'm going to switch it. So now I can say the tangent of theta is u over a, so our u is going to be a tangent theta. Is that okay? And our radical, I'm going to pair also with the constant. And so let's see, adjacent over the hypotenuse would be a cosine. So hypotenuse over adjacent is going to be a secant. So that's going to be our radical over the a, or we can say our radical, the way we're going to substitute that radical is with an a secant of theta. Okay, so what do we need here? So again, if we let theta go from pi over 2 to negative pi over 2, then we'll get our tangent is going to be any real number. We'll get anything we want out of that. And as long as we're again in quadrant 4 or quadrant 1, our secant, which...
Thank you, Randy High School. That concludes our drill. Again, that concludes our drill. Please proceed. Business as usual. Thanks.
I thought we talked about this. So this is 1 over cosine. Cosine in quadrant 4 and quadrant 1 is always positive. So we're saying the radical is equal to something positive, which is what we need. So it works. We don't have to worry about that. Okay? Now, the third one's where it gets more complicated. But I don't think we're going to get to the complication today. Maybe we'll get to it tomorrow. So the third one is if we have the integral of u squared minus a squared. So we're going to label our triangle. And since we have a subtraction in the radical, the way I remember it is whatever precedes the minus sign, we're going to call the hypotenuse. And one of the sides is going to be a, the other one is going to be the radical. And this is where I never remember what to do. I'm going to guess and see if that works. So if we connect our u, which holds the a in it, which holds the x in it, with our constant, that would be, let's see, opposite over hypotenuse would be a sine, so hypotenuse over opposite would be cosecant. We don't want a cosecant. We want a secant. Now, I told you I got this wrong all the time. So this is going to be the a, and that's going to be the radical.
So we want a in the denominator.
Yes. Yep. So now we have that secant of theta is u over a. So u is going to be a secant theta. Okay? And our radical, we're going to connect also with our a. So we're going to get the tangent of theta is the square root of u squared minus a squared over a. So we're going to say that our radical is going to be a tangent theta. Here's where it gets complicated. And we'll talk about this complication, but not today. So here, we want u to be able to be anything we can possibly be. So secant, which holds a cosine in it, is 1 over cosine. For cosine to do everything that it can do, we want to be able to go from 0 to pi. So we want the theta to go from 0 to pi. Now, pi over 2 isn't going to work because it's going to be undefined there, but we want to go from 0 to pi. That's going to give us all possible positives in quadrant 1, all the possible negatives in quadrant 2. The problem is we're saying that this radical, which we know has to be non-negative, is equal to a tangent. But a tangent in quadrant 1 is positive, which is great, but in quadrant 2 it's negative. So we'll see an example at the end of tomorrow, if I'm lucky, where when the limits on this integral come from some place that makes tangent negative, like in quadrant 2, then we can't say the radical is equal to the tangent over that interval, because that would be saying the radical is equal to a negative. And so what we will do, we'll have to be alert and say, oh, it's going to be a negative. So in our integral where we substitute for the radical, instead of calling the radical a times tangent of theta, we're going to call it negative a tangent theta, so that it is in fact always equal to something that's non-negative.
Can you do absolute value of tangent theta? Or is that a problem?
Yeah, that would be a problem as well.
Oh, okay.
Okay, anyway, don't worry about it yet. We'll get to, I'll tell you when to worry. So let's do an example of where this is really going to work. So let's look at an integral of 1 over x times the square root of 16 minus 9x squared dx. So first we should note that this is not an integral we can do using any of the techniques that we know. You know, we know substitution, we know integration by parts, we know all the integrals of the inverse trig functions. I say this aspirationally. We know partial fractions. I think that's pretty much it. Did I miss anything? Anyway, none of that's going to work here. So, but it does have a radical, so we think this is a great candidate for a trig substitution. So let's see how this works. Well, we look at the radical, and that is what drives how we're going to label a triangle, which is what I think is the hardest part of this whole operation. Because it's got a minus sign, whatever's in front of it, we're going to take its square root and call that the hypotenuse. And so that means we're going to call the hypotenuse 4. Now, this is our u squared. So one of these sides we're going to call 3x, and the other one we're going to call the whole radical. The question is, which order does it go in? What's that?
I vote the bottom.
You vote the bottom. So you vote that we call this 3x. Okay, I don't know about that. Because now, if we match the thing with x in it with a constant, this is adjacent over hypotenuse, we're going to be saying that's equal to a cosine of theta. Well, you had a 50-50 chance. That's a pretty good gamble. So we guessed wrong, which is how it would have worked if I had picked it. So we'll go 3x and call that the radical. You see how I'm deciding what works and what doesn't? Okay, it's got to end up being that this thing with x in it is equal to a sine, a tangent, or a secant. Okay, now we can say that the sine of theta is 3x over 4. So I'm going to say x is 4/3 sine theta. Are you with me so far? And I always have to solve for x because I have to get dx in terms of theta. So dx is going to be, now we're going to differentiate this. So we're going to get 4/3 cosine theta, and this is really dx d theta. And we're going to multiply that d theta to the other side. So when we go to substitute, everything we see in that integrand has to be replaced by something with thetas in it. And the dx is going to get replaced by this. All of this is going to be our dx. Okay. Now, we need an x. Well, we got that. So there's our x. We need a radical. So we come back to our triangle, and we want to partner the radical with a constant. And so that would be, it looks like a cosine of theta. So the cosine of theta is going to be that square root of 16 minus 9x squared all over 4, which means our radical, square root of 16 minus 9x squared, is going to be 4 cosine theta. Now we're cooking. Ready? We're going to make the substitution. So our integral is going to become, I'm going to put the dx in the numerator. So this dx, I'm going to put right up here, and that dx is 4/3 cosine theta d theta. With me? Any nods of heads? Okay, now I got to replace the x. The x is, oh, here it is, 4/3 sine theta. 4/3 sine theta. And the radical, there it is. Yep, it's a 4 cosine theta. Okay, all of the x and dx stuff was replaced by thetas and d thetas. The hope is this integral is doable. We can do this. So, well, we can clean up a little bit. Looks like those 4/3 will cancel. Looks like that cosine theta will cancel. This 4 in the denominator, we can pull that all the way out. call it 1/4 times the integral of, yeah, we're going to call that cosecant of theta d theta. This is an integral we know, I hope, is, oh goodness, it's negative natural log of the absolute value of cosecant theta plus cotangent theta plus c. You with me? We're not done. Now, we're going to go back to our triangle, and we're going to go from the thetas back to the x's that we had to start with. Ho, ho, ho. So we have negative 1/4 natural log of the absolute value of, let's see, cosecant theta is going to be, it's 1 over sine. Sine is opposite over hypotenuse. It's going to be hypotenuse over opposite, right? 4 over 3x. Okay? Plus cotangent theta. See, cotangent is opposite over adjacent. This must be adjacent over opposite. So that's the square root of 16 minus 9x squared all over 3x plus c. Kind of cool? Kind of crazy. Do you want a printed copy of the worksheet that this comes from? Or do you want, I'll leave it out. What I'll do is, I think I made some copies. And I will send them around. If you want one, you can take it. If not, pass
Is
the
this an
file.
example for this, or is this the sheet of homework's on?
This is the sheet the homework is on. So we're going to spend 2 days on this because I got lots more still to do. So this is just like an introduction. So we're going to do the homework. You aren't going to be able to do all of it. You can try a couple, see what you can do with it. We'll talk more tomorrow, or if you want to look at the videos on there, we'll go all the way through it. Let's see if we can at least get a start on another, on one more. Okay? How good are we? Let's do the integral of 1 over the square root of 4 plus 9x squared dx. So first appreciate that there is no way we can do this using techniques we have learned prior to today. And you can't do that with U substitution. It's not an inverse trig function. It's not an integration by parts. That would be awful.
Can't just like pull out the 9 and call it.
Nope, because you got the square root, right? So to be an arctangent, it couldn't have the radical. To be an arcsecant or an arc sine, it would need a minus sign. And we can't fix any of those.
Oh, well.
Can't be a U substitution. We don't have any x in the numerator for the du. So we're stuck. Well, that's okay. Now we know what to do with this. Because it's a square root of a plus in there, we're going to call the hypotenuse that whole radical. So it's going to be the square root of 4 plus 9x squared. The other two sides, one is going to be the square root of 4, the other one's going to be the square root of 9x squared. So it's going to be a 2 and a 3x. And this is what I always find the most challenging. So do we put the 3x opposite and the 2 adjacent, or the other way around? First option is correct. Because that will allow us to say that the x combined with a constant is going to be a tangent. And remember, we want either a sine, a tangent, or a secant. So we're going to say tangent of theta is 3x over 2. We're going to solve for x. So we're going to multiply by 2/3. So we have x is equal to 2/3 tangent theta. We have to get x so that we can get dx. So you'll get dx, you'll get the radical, and then you'll plug it in there and we're off to the races.
Awesome.
More to come tomorrow.